In this lecture, I want to briefly go over how to convert from a Newman projection back to a seesaw structure. So it's really just kind of working backwards, but it's good to go through at least one example. So let's go ahead and draw a Newman projection, and we'll kind of stick with I should draw the groups first, the blanks first before the bonds first before I start adding the groups. So let's draw something like this. Okay, that's a good Newman projection, fairly complicated. So what we want to do is convert to seesaw. And what you're doing is sort of building the seesaw from sort of going in reverse. We start just like we start with a dot with a circle around it when we're looking at a Newman projection. A seesaw structure is going to have two carbon atoms bonded together by a bond that's parallel to the bottom of the piece of paper, or the bottom of the screen in this case. We're going to add straight lines and wedges and dashes accordingly. However, what we want to do is be a little bit mindful. We don't want to just start throwing on wedges and dashes and straight lines. It needs to match the Newman projection. Well, what we first want to do is identify the I. So ID the I. What direction are we going to look down? Let's look, just because I have some space over here, let's put our I on the left side of our molecule and have it look from left to right. So we're looking right. That is that builds the foundation for drawing our seesaw structure, because now we have the dot, which is the first thing our eye runs into, and then the circle, the second thing our eye runs into. Then let's consider, just like before with seesaws, with Newman projections, let's consider the vertical substituents. So our dot has a vertical substituent pointing up, so we're going to have our straight line on that first carbon tetrahedral center pointing up. It's going to define where we put a wedge and a dash, and then we'll add that group. So that was the OH that was pointing straight up at the dot, is going to be for our first carbon. And then similarly, we're going to go back to the circle carbon, and connected to the circle carbon is a fluorine atom going down. So based on the tetrahedral arrangement, we're going to have that fluorine pointing down and to the right as a straight line on this tetrahedral center. And that defines the wedges and the dashes accordingly. So we're going to, I've kind of done step 3, but then we add the blanks, which are going to be wedges and dashes. So we add our wedges and dashes, and then we do wedges first. And so if we look right, the wedges are on the right. So recall that the Newman projection has a right side and a left side. Because we are looking to the right, and our I define that, then the wedges are going to be on the right. So that's going to be this kind of chicken foot looking thing, I guess. So you have just two lines hanging off of the bond that's connected to that dotted carbon. And then at the back, we've got a chlorine atom, a Cl, and so we draw that Cl atom accordingly. So those are our two wedge groups attached to the dot and the circle, just like kind of what we did with the Newman projection, except we're on the other half of the process. Now, similarly, we can go over to the dashes, and it turns out the dashes are both hydrogens in this case. We don't have to worry too much about what's connected to the dot and circle. Our I would get us there anyway, but our remaining blanks are just hydrogens. So I've done it. I've drawn a seesaw structure that had, with the correct orientation of the bonds and the groups attached to those bonds at both the front and back carbon atoms. Otherwise, all the little nuances you've seen with Newman projections also apply to seesaw structures.